Hi, in this presentation, we're going to be talking about science and measurement. So, what exactly is science? Science is a body of knowledge that's based on testable predictions and observations of the natural world around us. And science is also an activity, and humans have been engaged in science since way back before recorded history. Our most ancient ancestors, when they were observing the behavior of, say, animals and making predictions so that they could successfully hunt, or looking at the stars and making predictions about uh, the lunar cycle. We're engaged in science, so science has a very long human history. To talk about science, we have to define some terms that we use when we're talking about science. The first is a hypothesis. So, a proposed explanation for something we've seen, an issue, a question, or problem in the natural world. And our hypothesis is something we think explains this phenomenon we've observed. And to be a scientific hypothesis, there has to be a test for wrongness. So, for instance, I could make the hypothesis that the moon is made out of cheese. And that might be a really silly hypothesis, but it actually is a scientific one because we can test it and see if I'm right or wrong. And we could do that by observing the moon and making calculations on the gravitational field of the moon affects the Earth and vice versa. And then that could help us determine how dense the moon is. And we could say, well, is this density compatible with it being made of cheese or being made out of some other material? Or we could even do more direct observations and actually send people to the moon to take samples of the moon's surface and rocks, and we can see, are they made of cheese or not? And of course they weren't, so meant that my hypothesis that the moon is made of cheese, while a scientific one, was not valid. A fact in science is when we have some phenomena and we have a lot of different people observing this phenomena and they're in close agreement about what they see, we can say, okay, that's a fact. So we can say if we are holding an apple in our hand and we drop it, it's going to fall towards the earth. And this has been observed for thousands of years with not really anything to contradict it. So we can say that this phenomenon, things fall towards the earth if they're unsupported, is a fact. Also in science, we have laws. And a law is a hypothesis that's been repeatedly tested and again has not been found to be invalid or been contradicted. So, for instance, Galileo made some hypothesis on the movement of objects and the nature of matter in motion that he called inertia. Later on, Sir Isaac Newton looked at Galileo's observations and made some of his own and wrote the first law of motion, Newton's first law of motion. And again, this is in the hundreds of years since Newton formulated this law has not been contradicted. And then lastly, we have theories. And sometimes when we're talking in casual conversation, a theory kind of gives the impression that it's just somebody's guess or what they believe to be true. But in science, it's a little different. In science, we have theories when we have a whole bunch of hypotheses that have been well tested, not contradicted. We have a ton of observations by various observers. And we take these hypotheses and these observations and we kind of stick them all together and we come up with an overarching theory that explains these hypotheses in this phenomenon. So you can think of things like the cell theory in biology that explains how living matter behaves, or things like Einstein's theory of relativity that describes how matter and gravity interact. The scientific method is a way of gathering and organizing knowledge. So, to kind of increase our base of scientific knowledge, we have to look at problems, do some observations and experimentations, test our hypotheses, and then check our results before we can say that we've actually added to our basis of scientific knowledge. Some common steps in the scientific method are first, we look around the world and we see something that puzzles us. We have a question about some type of phenomenon, some type of unexplained fact that we've observed. And then we're going to make a hypothesis. that we think explains what we've observed. And then we can predict, okay, if the hypothesis is true and we do a certain experiment, we should get this result. And then we're going to perform those experiments, or in some cases, we'll do calculations to test our hypothesis and to see if our predictions were correct. And if they were correct, then we can formulate the simplest general rule that makes sense of what we observed in steps 2 through 4. And all scientists should share what we call the scientific attitude. And this is one of curiosity about the world around us, kind of push to have this questioning attitude about what we see around us. And also, we want to experiment to see, to find out why things are happening. We can make our hypothesis and test it. The scientific attitude also has to be one of, if our experiments show that we were wrong, we have to be willing to admit that error. We have to say, okay, my hypothesis was not valid. We need to go back a step and try to figure out a hypothesis that does explain this. So scientists have to be experts at changing their minds and accepting experimental findings, even if those findings kind of invalidate a hypothesis that was very dear to them, that they truly believed in. And so a scientist also has to be willing to consider other hypotheses that explain what's going on, even if it's not the one that they originally accepted. So there's several ways that humans have developed to look at the world. We've talked a little bit about science, the study of natural order and the discovery and recording of natural phenomena in the world around us. But we can also look at the world through the lens of art, which is the interpretation and expression of human experience. And then we also have religion. And whereas science is more involved with the natural world, religion is involved with the spiritual world. And most of the time, religion also involves belief in and the worship of a being who is not part of the natural world, as a supernatural being. There's some similarities between art and science. They both are concerned about what is actually possible in human experience, what's actually possible in the world around us. And to have a basis in both art and science can expand how we can view the world and make decisions about the world around us. And if we don't bother to learn about one and concentrate solely on the other, we're literally cutting ourselves off from an entire world of human experience. There's also similarities between religion and science because both of them deal with unanswered questions about the world around us. And again, if we have an unanswered question about natural phenomena, science is probably the best way to find out the answer. But if we have maybe a question about a moral or philosophical or spiritual issue, then a lot of people will turn to religion for those answers. Another two terms that sometimes people get confused is science and technology. So we've talked about science being the gathering and organizing of knowledge of the natural world. And it's kind of can be almost an abstract activity in some cases, or an idealized activity. But technology is taking that scientific knowledge and using it for practical purposes. So maybe to improve our lives or to entertain us or to keep us safe or to improve our health. Okay. And also technology provides the tools so that we can further explore scientific concepts. So for instance, if we didn't have um, infrared or radio wave detectors, our astronomical knowledge would be severely limited. So that technology has helped us increase our abstract scientific knowledge. So let's move on to scientific measurement because to know about something, a lot of times you have to be able to measure it. In science and physics, we usually use what's called the metric system or the Système International. And the metric system is based on powers of 10. And again, it's the standard for science. And if you look at our little graphic here, all the countries in gray use the metric system, And the countries in red are still the only ones that use what we call the imperial system. So the United States, they're on the west coast of Africa. You can see Liberia, and then in Southeast Asia, Myanmar. And these are the only three countries that still use a system other than the metric system. We measure things in feet and yards or gallons and quarts or pounds and ounces and things like that. In the metric system, we have several basic units of measurement. So if we're going to measure length, we're going to use the meter, and the meter is a little bit longer than a yard. If we're going to measure the mass of something, we're going to use the gram, and the gram is pretty small. It's about 3/100ths of an ounce. And then if we're going to measure volume, for instance, of a gas or some type of liquid like Coca-Cola or something like that, we would measure it in liters. And 1 liter is a little bit more than a quart in our measurement. Again, the metric system is based on units of 10. So if we're converting from a larger unit to a smaller one or vice versa, this makes it really easy. Basically, all we have to do is move the decimal point. So if we want to find out how many centimeters are in a meter, we just have to move a decimal point. Whereas if we want to find out, for instance, how many inches in a foot, we have to divide by 12, or how many inches in a yard, we have to divide by 36. So it's a little bit more difficult. So here we see our basic unit, and let's say, we're talking about a meter. If we're going to talk about 10 meters, going to the left there, we can say it's a decameter. If we're talking about 100 meters, we can call it a hectometer. And then if we're going to talk about 1,000 meters, we'll call it a kilometer. And as we move to that larger unit, we just move that decimal point to the left. And then if we start with our basic unit of a meter and go to the right to talk about smaller units than a meter, if we're talking about 1/10 of a meter, it would be a decimeter. If we're talking about 100th of a meter, it would be a centimeter. And if we're talking about 1,000th of a meter, it would be a millimeter. Okay. So for instance, again, 1 kilometer is 1,000 meters. 1 millimeter is 1,000th of a meter. If we have liters, if we're measuring a fluid, um, 1 liter is composed of 1,000 milliliters. And milliliters is a very common unit. You're going to see in healthcare, we measure a lot of fluids and medications and things of that nature in milliliters. So let's do some basic conversions here. If we have 140 centimeters, how many meters do we have? So we look at centi here on the right, and we see it's 100th of a meter. So we're going to want to move the decimal point 2 places to the left. And so 140 centimeters is 1.4 meters. And then if we wanted to know how many millimeters this is, we would move the decimal 1 point to the right. So 140 centimeters would be 140 millimeters. So you can see this is much easier than trying to convert, say, feet and inches and yards or ounces and pounds and things like that. So let's try some problems. And I'll give you a minute after each problem to try to work it out on your own. So let's say we have 5.63 kilometers. How many meters would that be? Okay, so we know that, okay, kilometers is 1,000 meters. So if we want to find out how many meters is in that number, we're going to move our decimal point 3 places to the right. And so we're going to have 5,630 meters and 5.63 kilometers. So let's look now at 7,698 milliliters. How many liters would that be? So we know there's 1,000 milliliters in the liter. So we're going to move our decimal point, which starts behind the 8 there, and move it 3 spaces over to the left. And so we would have 7.698 liters. So if we have 419 millimeters, I'm sorry, millimeters, I was correct, is how many centimeters? So a millimeter is a thousandth, where a centimeter is a hundredth. So we're going to move our decimal point one place to the left from behind the 9 to behind the 1, and we'll have 41.9 centimeters. Our next problem is 825 grams is how many kilograms? Okay, so we know a kilogram is 1,000 grams, but we can look at 825 and we can see that's less than 1,000. So our number in kilograms is going to be less than one. And again, with the 1,000 grams in a kilogram, we're going to move the decimal from behind the 5, 3 paces over to the left. So that's going to be 0.825 kilograms. And then our last one is 67.2 centimeters is how many millimeters? And again, a centimeter is a hundredth of a meter, millimeter is a thousandth of a meter. So we're going to move our decimal one place to the right, and our final answer is going to be we're going to have 672 millimeters. So let's talk now about scientific notation. When we're in science, a lot of times we are dealing with numbers that are extremely huge. Like think about the diameter of a galaxy, which is hundreds of millions of kilometers. Or we're dealing with numbers that are really small. Think of the size of a virus or something like that. So scientific notation allows us to take these huge numbers and write them in a really compact way. And it uses the powers of 10. So for instance, instead of writing out 1 million, I can write 1 times 10 to the sixth. And the way we determine that is when we're writing numbers in scientific notation, we always want to have one number in front of the decimal, and then the numbers that we end up with behind the decimal will be our exponent. So to write 1 million, I would put my decimal right behind the 1. I can count my digits 1, 2, 3, 4, 5, 6, and that gives me my exponent. So I'll have 1 times 10 to the sixth power. We can also write very small numbers this way. So if I have a number 0.002 and I want to write it in scientific notation, again, I want to have one digit in front of the decimal. So I'll move my decimal all the way here behind the 2, and then I'll count how many places I had to move that decimal. 1, 2, 3. And since I'm moving the decimal to the right, it's going to be a negative exponent. So that number is going to be written as 2 times 10 to the negative third power. Okay? And when we're converting numbers from scientific notation back to conventional numbers, the exponent tells us again how far to move the decimal point. So if I have this number written in scientific notation, 2.7594 times 10 to the third, and I want to write it in conventional numbers, I'll just move my decimal 3 places over, 1, 2, 3, and I get 2,759.4. And the same thing with our negative exponents. If I have 1.36 times 10 to the negative third, well, now I need to move my decimal the other way. So I'm going to move it 3 spaces to the other way, and my conventional number is going to be 0.00136. So let's try some problems with scientific notation. So if I gave you the number 17,452, how would we write that in scientific notation? So again, to write this in scientific notation, we'd want a single digit in front of the decimal. So we'd put it right there behind the 1. And then the number of digits we have behind the decimal will tell us our exponent. So this number would be 1.7452 times 10 to the fourth power. So how would we write 4 in scientific notation? Okay, this problem is a little tricksy. So if we're writing the number 4, we only have a single digit. So we're not going to need to move our decimal point at all. So if we actually wrote this in scientific notation, it would be 4 times 10 to the 0 power because we're not moving our decimal at all. So how about our next problem? 0.09 in scientific notation would be what? And here we have a number smaller than 1. So we want to get a digit in front of the decimal. So we're going to move our decimal 2 places to the right. So it's behind the 9. And then so in scientific notation, this number would be 9 times 10 to the negative second power. So let's change the numbers from scientific notation back to conventional numbers. So 8.597 times 10 to the third would be written how? Okay, our exponent 3 tells us how many places we're going to move our decimal. And since it's a positive number, we'll move it to the right. So we would end up with 8,597 in conventional numbers. How about 5.9 times 10 to the first? Again, our exponent tells us how far to move our decimal, so we're only going to move it one place. So 5.9 times 10 to the first, written conventionally, would be 59. And then our last problem is 3.7684 times 10 to the negative fifth. And since this is a negative exponent, we're going to have to move the decimal the other way. So our final number here is going to be 0.0000376684. So a very small number. I have the answers here if you wanted to go back, if you struggled with one of these problems, if you wanted to go back and test yourself again, the answers are right here. Hope you enjoyed this presentation on science and measurement, and our next presentation is going to be about Newton's first law.